Differential equation. Halves. Taylor polynomials. Infinite series. Differential equation.
Welcome, everybody. We are continuing our AP Calculus BC exam prep for the 2020 year. We're so glad that you're joining us today. Today, we're going to be talking about approximating solutions using Euler's method. But throughout today's lesson, we're going to be not just looking at some Euler's method type FRQs, we'll be also looking at how this might connect with other AB and BC topics on this year's 2020 exam. So if you haven't done it already, don't forget at the bottom of each video, you'll see the little link there where you can access our resources. You'll see a little folder that says Isaac Newton has shared that with you. You can download those, print them off, follow along with us. And as always, there's a whole bunch of additional problems in those materials that we will not get to during our live lessons. And all of those problems are unique, new, and designed specifically for that conceptual understanding to get you ready for the 2020 AP Calculus BC exam. So my name is Brian Passwater. I am here joined by my awesome co-host, Tony Recker. Tony, how's it going this morning?
I am doing fantastic. The sun is shining here in the Midwest. We have a great lesson here over Euler's method, and we're joined by a few thousand of our closest friends who are studying BC calculus, both on the teacher side and the student side. So I couldn't be better. And I did my homework. Brian assigned me a homework assignment where I was supposed to use a image of my favorite movie of all time and use it as my backdrop. So here it is. What do you think?
Yeah, so I've been giving you some homework assignments, and I think I got this one already. So last time it took me the whole session, but I'm pretty sure I got it figured out. I'm going to go with because you're a musical guy, right? You play the guitar. You've been in lots of bands. I've heard you sing. I've heard you perform. And so based on that, I'm going to guess, and you're pretty old. I'm going to guess. I'm going to guess Sound of Music is my guess.
Okay, well, you're close.
I get it? No?
It's an outside rolling meadow. Yeah, that's my wife's favorite movie. However, this is not a scene from The Sound of Music. If you look closer at the animals, that might give it away. I'm not so sure there are too many of these animals in Austria, perhaps. But I'll give you another guess or two later on.
Okay, do me a favor. Maybe did you have any other like backgrounds? Because I'm already thinking I'm never going to guess this. Do you have anything else queued up that later on you can give me like a second hint or something like that?
I tell you what, I think I can find one while you're doing a problem later on. So I'll make that deal with you.
Perfect.
I can do that.
Okay, so I'll think about it some more. Until then, do you want to get us going on what we're looking at today, this week, and then coming up?
I sure can. What we have got going on today, obviously, is Euler's method. And looking ahead to the next couple of days in the week, we're going to follow that up with logistic growth tomorrow and arc length on Friday. And it's really important that you understand that we're going to really work hard to take previous ideas that we've talked about already and embed them into these newer ideas. So even throughout today's lesson and on into this next week and even beyond, you're going to see, say, convergence and Taylor polynomials, maybe some integration techniques possibly infused into some of these newer ideas. So you don't want to just look at the upcoming calendar and say, I know everything there is to know about logistic growth, because you can see how we merge some of these ideas together and we create this more evolved free response question. So keep that in mind as you are moving through. As we look into the future, we know that May 12th is our AP exam. We know that it's going to consist of 2 free response questions. So you always want to keep that in your mind, and we'll go into a great deal more of detail with that test structure as the test draws near. As far as today's lesson, it is centered around a wonderful mathematician named Leonard Euler. It is pronounced Euler, not Euler as in Bueller. He is a Swiss mathematician, and he just had so many contributions to the mathematics world. His mathematics that he did applied to physics. He wrote treatises on shipbuilding and optics and acoustics and astronomy and mechanics. So he's certainly renowned as one of the greatest mathematicians of all time. And in fact, I think it was last week that Brian had a list. He composes a top 50 list of his all-time favorite mathematicians, and sometimes they fluctuate. So Brian, where does Euler fall on your list?
Yeah, he is one of my all-time favorites. I love the last line on the screen that says he's regarded by many to be the greatest mathematician of all time. He actually comes in number 4 in my top 50 list, and I put that in the Dropbox, I think, last week when we talked about my top 50 list. So he definitely is in my top 5. So many amazing things about him. It's kind of interesting because he gets this Euler's method, credit for this. But this is not even near the peak of all the things that he's contributed. I think I remember that he is the most prolific mathematician of all times in terms of producing volumes of work and papers. And so, but even with all that genius, all of that incredible talent, I think my favorite thing about Euler, my favorite anecdote was I remember reading one time, and I hope I have the right guy because we didn't plan this out. So it's always tricky when you're going live on the air because you might say something that's wrong, and then we get all of those emails correcting us. But I remember reading, Tony, and tell me if I'm wrong, that there was a time when he got really old and he lost vision. Like he ended up going blind, but he was still doing a lot of mathematical work because he had such a photographic memory. He would just dictate to his assistants or his students or whoever was helping him, and he could have everything kind of memorized and know where he's going, and they would just write, on paper everything that he was doing. So he was still producing mathematical genius as a blind mathematician later in life. Does that sound
Very,
right, or am I off
very
track?
true. I've read that same thing about him. I've read that same thing. And
Okay,
students,
good.
you may not know this, but I bet your teachers do, but many of you students do know the number E is called E for a very important reason. It's this guy right here. So, all right.
Oh, I thought they called it E because it used the letter E for the symbol.
Yeah.
So yes. Anyway, so Euler's method we're going to talk about today. And so Euler's method, and we're not going to, during these review sessions for the exam, we know that you've already covered these materials, right? So in the previous 2.5 weeks, we were teaching lessons from Unit 9 and Unit 10, parametrics, convergence, and Taylor polynomials, because we knew that a lot of schools, and most schools probably, didn't get a chance to cover those topics before students were sent home for distance or e-learning. And so the College Board wanted to make sure that you had some lessons to introduce those topics to you. And this review stuff that we started this week and that will continue all the way through during the rest of these sessions are a little bit different in nature. That's why Tony and I are co-hosting these, but these are covering topics that we're assuming you have covered before, right? And so we're not going to be teaching a brand new lesson. So you're not going to see us teach Euler's method today from scratch. We're not going to teach logistics or arc length or things like that because we know that you've probably had them. And we're going to kind of just jump right into AP exam review. Now, if you're thinking, oh my gosh, we learned Euler's method a long time ago, I've forgotten that. Well, we're going to, in our examples, refresh and remind you how to do it. But there's a reason why we're not going in depth with our lessons. And so Euler's method is a numerical approach to approximate a particular solution, right? We've done differential equations, and in AB, we learn how to separate and integrate, right, to solve particular solutions or even general solutions for differential equations. But there's a lot of differential equations that you can't solve for, or you don't have enough information to solve them. And so in that case, how do you find solutions or approximate stuff? Well, we do that. One way is using Euler's method. And what it does is it takes a nice little twist. I always think it's like an intermediate between tangent lines and Taylor polynomials, right? Where you take a tangent line approximation. A tangent line approximation would be, I suppose, an Euler's method of 0 steps, right? But it's an Euler's method idea where you can take a tangent line to a graph, and then we realize that this graph keeps curving, right? The graph is changing. Once we pick our tangent line, we're sort of locked in. We don't have a way to adjust. And so the further out we go from that point of tangency, the less accurate we get. But then instead of being stuck on this path forever, we're able to sort of stop at our own discretion and then readjust our tangent line to say, well, this tangent line is not going so well, but I can adjust my slope. So this graph had a different slope, right? The graph is turning, and the graph now has a tangent line here. Well, I don't know what that point is on the graph, but I can maybe figure out the slope since I have the derivative. And so I can, from that point on, recreate a new tangent line, and we can keep adjusting these tangent lines because we have the derivative, and we can take our tangent line, we can come up with this little value, this point on our tangent line, and we can use our derivative equation to readjust the slope, create a new tangent line, and we can keep doing that indefinitely, and it kind of mirrors the shape of the graph, right? And how often you switch your tangent lines is called the step size of the Euler's method problems. And so Tony and I today are going to be looking at a couple of these problems in context of the AP exam, and we do it very differently. And as we were planning these sessions, we had some discussions of should we try to be uniform in how we tackle, how we approach these problems, but we decided no. So we're both going to do these problems how we show our own students. And so we're doing that because we know there's a lot of different ways teachers approach this topic. And so if I'm doing it one way, it might look familiar to you. We might be like, that's not how I learned it, right? So when Tony does his method, that might make more sense to you, or vice versa, right? And so we're going to do them both ways so you can see the different approaches. They're both valid, they're both perfectly correct. If you like, or if you've done my approach before, then when Tony's doing his example, see if you can see what he's doing, because I think it'll make it a little bit more understandable and help on the ideas more if you can go back and forth between our two methods, right? So don't be too caught off guard if we're doing these a little bit differently and how we set them up, but we're doing the same thing in the background. We're both using those tangent lines. So this is a traditional FRQ covering Euler's method. This is what you might have seen in years past, right? It might say something like, consider the differential equation dy over dx equals 4x squared plus y, and y equals x of x is the particular solution with the initial condition f of 0 equals 2. Use Euler's method. They kind of give you that suggestion. Starting at x equals 0 with 2 steps of equal size to approximate f of 1. And so this is a good example because in our A, B, and BC classes, we don't have a way to solve that differential equation. We can't separate, we can't solve it to find a general solution. There are techniques to do that. You might have heard about integrating factors or other ideas, but we can't solve it with what we know in Calc A, B, or BC. And so we can't find f of 1, and we don't even know what the graph of f looks like. But let's just say for our purposes, the graph of f looks something like this, right? Let's just pretend it looks something like that. And all we know is the derivative and the starting point, right? We have f of 0. And so what we're going to do is we want to approximate f of 2. We want to know, what is f of 2 on this graph? And so we can take our tangent line idea and say, well, we could make a tangent line here, right? Because we have a point and we have a derivative, so we can find the slope. But then instead of just using that tangent line, knowing the graph of f could make a lot of twists and turns and our tangent line may not be very accurate, what if we adjusted, right? We have 2 steps. What if we adjusted halfway through and then redirected our graph to take on the shape or the direction of our original function, right? And so we can do that because on the original graph, we're going to be able to figure out not what that point is on the graph, but at least what the derivative is when x is 1. And so we can use this, and then we can figure out what this point is right here. So this is what we're going to be approximating. We're going to approximate f of 1 by coming up with, and I already realized I drew this wrong, didn't I, Tony? It should have been 0.5 and 1. We're doing 2 steps. I was thinking f of 2. I think I saw 2 here, and it got me a little bit mixed up there. So Tony, feel free if I do something wrong, you can go ahead and stop me and correct me, because otherwise this will be living in infamy. I don't want to do a whole problem wrong like I did a couple weeks ago on live YouTube channel. And so here's how I like to set these up. Now that we have this visual idea, I'm not going to draw that graph every time, but I want to remind you kind of what's happening behind the scenes, because we're going to get into a lot of formulas and things like that. And sometimes we lose track of what we're really doing. And so I like to use what I call the box method. And you might have your teachers do this. And Tony will show you another method that looks a little bit different, but really is doing the exact same thing. So I create this box and I call this top row in, and then the second row is going to be my x's, so x sub n, and then y sub n. And then depending on how many steps we have, that will determine those n values. So we always start at n equals 0. That's your starting n value. And then we're doing 2 steps. So we're going to go 1 to 2. So this is kind of which step you are on as our n value. And then our x sub n would be the x and y coordinate, right? So we're starting right here. So we know that x was 0 according to our coordinate and y was 2. And then now we want to come up with what that next point is on the line, because we're going to figure out what that first kind of halfway point is. And so the step sizes, if we're doing 2 of them and we're trying to approximate f of 1, we know that our last x coordinate has to be 1. That's what we're trying to get to. So if we're doing 2 steps, starting at 0 and going to 1, then the middle step, x has to be 0.5, right? Because it's going to be equal size steps. So it's going to be 0.5 and then 0.5. And so we can always figure out our x values pretty much right away. The trick is finding out what those y values are, right? And so we have this little formula that if I want to know the next y value in the box, we'll call that y sub plus 1. That's always going to equal your current y value plus your step size, which we're going to call this h, will be our step size, times the derivative at your current location. You might recognize this. It looks kind of fancy and complicated, but really this is just a tangent line equation, right? We have our y is going to be our initial y value plus the distance we travel times the slope. So really this is just another way of doing tangent lines. So when Tony does his approach, you're going to see pretty quickly that he's doing that exact approach, but in a more direct way with tangent lines. And so if I want to find y sub 1 in this case, it's going to be my initial y value, which was 2, plus our step size, which was 0.5. That's what h is, we said, right? H is 0.5 because we're doing 0.5, 0.5 each time. And then we have to find the derivative. This is the big key, is we use this differential equation for our slope. And so we're going to find the derivative at your current location. So we're using this green tangent line. So x is 0 and y is 2. So our derivative when x is 0 and y is 2 is going to be 0 plus 2, which is just 2. And we get 2 plus 1 for a total of 3. So our y value here is going to be 3. And then we're going to do it one more time. So if I want to find y sub 2, my last y value, now we have a new y value. Now we're sitting right here, right, on this point. So my current y value is now 3. And then our step size never changes. It's always going to be 0.5. But our derivative now is different, right? We have our equation 4x squared plus y. But remember, we have this coordinate here. Our new coordinate is 1/2 comma 3. And so we have to plug our current point 1/2 comma 3 into our derivative and then evaluate that. And so if this was a multiple choice question, which a lot of times they have been in the years past, we don't know exactly what this year's exam is going to look like, but I would be pretty confident in saying this will not be on this year's multiple choice test. I'm sure Tony would agree, since we have no multiple choice tests this year. 4 times 1/2 squared is going to be 1 plus 3, and then 3 plus 1/2 times 4 just gives us 5. So our value here is going to be 5. And so that's what we just calculated right here, which tells us that f of 1, according to Euler's method, is going to be approximately equal to 5. Right? So this is kind of one method to do. It's going to be really important, especially with free response questions, that if you use a table or use this method or use the method that Tony's going to show you here in a second, make sure your work is labeled, organized, and clear what you're doing, right? You're telling a story with your work, right? You're trying to tell the person grading your paper what you were thinking, what you were doing, so that way we can award you all the points that you deserve. So I mentioned, Tony, that this is probably not going to be on this year's multiple choice, seeing how there's not a multiple choice. But this was a traditional FRQ. I'm thinking this might look possibly a little bit different this year. It might look like this, or it may look slightly different. Would you agree with that?
I would certainly agree. And as we move to our 2020 FRQ practice, when you see BC1, I think it'll be very evident just within the first line of what that difference is going to entail. So if you look at this and read it together with me, it says, let K be a constant. Well, there you go. Consider the differential equation dy dx equal kx squared plus y, where y equal f of x is the particular solution to the differential equation with initial condition f of 0 is 2. So it reads very similar to the problem that Brian just did, but instead of that 4 coefficient in front of the x squared, we have this arbitrary k. So now any kind of computer algebra system manipulator won't really get the job done in terms of trying to program in some kind of a sophisticated algorithm to figure out this particular solution. So our directive in this problem, using Euler's method, start with x equals 0, 2 steps of equal size. What we're going to do is, and I'll make sure I share my screen so you can see this. You're probably following along with your paper, but hopefully now you can see the screen where this dy dx is now k x squared plus y. Right, here's our differential equation. And you can see the difference here is the fact that we have that k. All right, so what we want to do is use Euler's method starting with x equals 0 with 2 steps of equal size, and knowing that f of 1 is approximately equal to 17/4, we got to kind of backtrack and figure out what that k is. So like Brian said, we're going to show you a couple of different methods to set this up. Both of these methods I use in my class, the one, a very similar one to what Brian uses. And then I also tend to use this one for some kids that might have a hard time with the structure of what Euler method is all about. And this is going to favor the kids who maybe are really good at writing equations of tangent lines, but have a hard time piecing together what Euler's method means. So we're going to start off with our point. We are given a point 0, 2. Right? That's our f of 0 equal 2 that was given. And we are going to figure out what the slope is. Well, we would hope that any good BC Calc student, any good AB Calc student would know that the slope is the derivative. So if we go to this derivative equation, dy dx, and we use the fact that the x is 0 and the y is 2, we'll very quickly come to the conclusion that k times 0 squared plus 2 is going to give us that slope of 2. Okay, well, what can you do with a point and a slope? You can certainly write the equation of a line, and it is a tangent line at that point. And this one's a pretty easy one to do because don't we really just have a y-intercept there? So what we could do is just use y equal mx plus b, right? A little bit faster maybe than using point slope form, and only because we have this 0 there. All right, now this is where things start to get a little interesting because we have to acknowledge this idea of the step size. So if we read back, we see that there are going to be 2 steps of equal size. We start at 0, we want to end at 1. You basically find the difference between 1 and 0 and divide by how many steps, and that will tell you that your step size is going to be 1/2. Okay, so that's going to indicate that our next point, our next row, our next iteration will have that step added to the x. So you always want to add the h to the x value in this particular point. Now we have to address, well, what is that y point? Well, we take that new x and we apply it to our previous tangent lines equation. So sometimes I might write another column over here and I'll call it the new y value. And the new y value here is just a matter of, like I said, replacing the x with, replacing the x with my newer x 1/2. And we end up with 3. And that's going to get carried over here. And that's really it. Right? That's the process. You just repeat it as many times as you need. So we go back into the slope. Now something's very interesting is going to happen to the slope now. If we let the x be 1/2 and square it, we have a 1/4 that's going to be multiplied by the k. We don't lose that k value now. And of course, we add the 3, right? We still plug the 3 in for the y. Now that might seem like a very unusual slope. Well, let's be honest, it is a very unusual slope, but we stay the course. We have to use the point slope formula now. So y minus the y1 equals the k value multiplied by the quantity x minus the x1. And so now we have a brand new equation of a tangent line, albeit a little weird in terms of this k. I just really briefly want to talk about notation here. I had a professor one time in college that was not very happy about students organizing their work with Euler's method like this because we're using a new instance of y and x that depicts a completely different tangent line. And so we were directed to maybe use subscripts, use subscripts of 1 for the first iteration, use subscripts of 2 for the second iteration. I don't necessarily require that my students do that. It is a more powerful, stronger way to communicate what you're doing. I don't see that on the AP exam that you would have to do that. If you think about this as being a restart for each of these steps, you're certainly going to be fine. But if you want your notation to be a little bit more prim and proper, the use of subscripts is not a bad idea. Once again, we're going to apply that step size of h, which is a half, which takes us to our x value of 1, which is a good thing, right? Because this is the value that I guess we're used to like solving for, right? But the problem is we know that value, right? We know that that value is going to be 17/4. That's the approximation that was given to us here in the question. But we want to figure out what is the k that's going to make that happen. So if we revisit our previous equation of our tangent line here, right here, we can then solve that for k by using this 17/4 as that new y, where 1 is our x. So what would that look like? Well, you could say something along the lines of f of 1, we know, is an approximation of 17/4, which means that that is really the same thing as y2 evaluated at that 1. Well, if I go ahead and rethink what this y2 expression looks like, I have 1/4 k plus 3. Now, this x2 is going to get replaced by that 1. 1 minus a half is a half. And then I don't want to forget that there was this minus 3 in the front that I'm going to add over here to that side. Okay, so what do I have here? If I just scroll down a little bit, I'm going to bring down that 17/4. And then I'm going to work this expression out. Well, actually, what I'm going to do is I'm going to subtract 3 over from this. We just want to be careful because really at this point, it's just some simple algebra, but simple algebra is also just as easy to mess up as complex calculus. So 17/4 minus 3 is going to be, I believe that would be 5/4. That 5/4 that we have there, let's multiply the 2 over. That way we get 10/4 or 5/2. And now we can solve this for k hopefully pretty easily, right? We'll call this 5/2. He's going to have a dream. I'm dreaming about being called 5/2. How's that? And if I subtract 3, which is 6/2, right? So 5/2 minus 6/2, 6/2 is negative 1/2. And then my final step would be to multiply both sides by 4. And we see that k is -2. So it's a very similar process that what Brian showed. It's just structured a little bit differently. And of course, it's now under the guise of a slightly different style of FRQ that is going to involve finding this value of k. So I think Brian's going to go ahead and take you through BC2, if I'm not mistaken. Is that right?
Yep, absolutely, Tony. Thank you. So I'm glad that you guys got to see two approaches because they really are the same thing. And if you understand Euler's method, then you can make those connections, because in a lot of the previous years, you might see some multiple choice questions where we're not going to see your work or how you're organizing things. And you can get to those answers pretty easily. Sometimes you guys can do it in your head, kind of some scratch work. But now, since they're all FRQs, you would certainly have to show your work in a very organized manner, but also we're going to have some more conceptual problems where having your work organized is not just going to help you be eligible to earn the points. It's going to help you solve problems that look a lot different than a typical problem. And so BC2 is an extension of what Tony did, where this kind of K values in, but kind of in a unique way. And so being organized, I think, is going to play a big role in making sure we can get this problem correct. So I went ahead and kind of created my table on here from before, and then I wrote our little kind of model equation that we're going to use. And so we have this table of values, a lot different approach. So we don't have a lot of information, but we're given different information than we normally have, right? Normally, we have our X values and our step sizes, and we're told what to approximate, whereas in this problem, notice the table, they actually gave us all the y values, right? They told us what the answers were. So we're not really approximating anything. We're trying to solve some other stuff in the problem. So we have this new differential equation, k times x minus y minus 2x squared, where k is a constant. And then we also know there's this condition, f of 0 equals 1. So we're going to use Euler's method with two equal step sizes h to approximate f of b. So now the problem is we don't even know what it is we're trying to approximate. Since we don't know what we're trying to approximate, we don't know how big our step sizes are. We have no way of knowing what h is. And so we're going to figure out if we can solve for h and k without even knowing what b is. And so now that we've seen a couple of examples with Euler's method, we can cruise hopefully through this problem through the Euler's part to get to solving for it, right? And so if we were trying to use Euler's method, what would we do? We would first try to figure out our y sub 1, right? We have our y sub 0 given to us. Our y sub 1 would be our initial y value plus h times the derivative, right? That's how we would set this problem up. Well, in this case, what do we know from this problem? Well, we actually know what y sub 1 is. In this table, we're given those values. So let's just go with it and see what happens. So we know that y sub 1 is 1/2, and that's going to be our current or our original y value plus h, which we don't know, times the derivative at the point 0, 1. So if I plug in 0 for x and y for 1 into our formula, look what's going to happen if you plug in 0 for x. Those are going to go away, aren't they? And all we're going to have left is this negative y term, which we actually know, right, don't we? Because we were told y in this guy. I'm so used to putting y there. We know that y is 1, don't we? So it's just going to be negative 1. So that means that we have 1/2 equals 1 minus h. And then if we solve for h here, we're going to get h is 1/2. And so what did that do for us? Well, first of all, it solved for 8. H is 1/2, which means my step sizes are 1/2. So that means my next x value then has to be 1/2, which means the last value up here is going to have to be 1 because we're going a 1/2, 1/2 each time, right? And so really this problem was having us approximate f of 1. Now, there's still one last piece that we haven't solved for yet is we have to solve for k, right? What was this k value here? Well, how can we figure that out? Well, now that we know what our last point is, we could use that to find our k value because we also know that y sub 2 is going to be y sub 1 plus h, which we now know is 1/2 times the derivative at x sub 1, y sub 1. And then we have all this information that we can now plug in. We know what y sub 2 is. We know our y value is going to be 3. Our current y value, y sub 1, is just 1/2. And then times 1/2 times the derivative. Well, let's go ahead and plug in what we know, right? We're sitting here at this point right here when x is 1/2 and y is also 1/2. If we plug that in there, we're going to get 1/2 times k minus y, which is also 1/2, and then minus 2 times x squared, right? So if you look at that equation, there's only one variable, k. We have everything else we were given to us. So we can use this to sort of work backwards to find that missing k value. And so if I'm solving this, I'm probably going to do this first. I'm going to work inside of these brackets a little bit. We have 1/2 k here. 2 times 1/2 squared. Well, 1/2 squared is just 1/4 times 2 is 1/2. And so really we have a negative 1/2 minus another 1/2, or just a minus 1. I don't love working with fractions. So whenever I see them, one of my first go-to moves is just to multiply through to sort of clear out those fractions, right? And so multiply both sides of the equation by 2, and we get 6 equals 1 plus this 1/2 is going to just cancel then, right? It'll become 1. 1/2 k minus 1. Hey, those ones cancel as well, and we just get 6 equals 1/2 k, which means that our k value is going to be 12. So kind of a neat twist on Euler's method, because you're not going to be able to Google or search that kind of problem on a app on your phone or something, or find the answer in a textbook, but really still using Euler's method, making sure that you can do it in a reverse kind of manner, right? So I love that problem. And so Tony's going to walk us through multiple parts of a problem. So now that we've seen a few, kind of 3 examples of Euler's method, Tony is going to look at a really cool FRQ that goes through a lot of different parts that connects Euler's method to a couple other things that we've been talking about.
Yes, and I think what I'm going to do with my part A, I'm going to accelerate through it a little bit, maybe show you the first couple of iterations, because I think you've got the general idea about how this is an iterative process, and you have to kind of repeat the same things over and over again to get to your result. Because I'd like to get to the parts that have the sort of the infused or embedded ideas from some previous topics. So if we take a look at the stem here, the function f is differentiable for all values of x. We know that f of 0 is 6, and we're given this random f double prime of 0 equals 1/4. I bet we use that at some point. A portion of the graph of f prime, the derivative of f, is shown here to the right, and the regions bounding, the bounded regions R and S have areas of 1/2 and 5/8 respectively. Part A just is a straightforward Euler's method. Start at x equals 0, use 4 steps of equal size, and approximate f of 2. Well, if we set it up structurally like I did before, we would start with this initial 0.06, and then finding the slope is really the nuance with part A as opposed to what we've seen in the previous couple of questions. Since we're given a graph of f prime, the students would have to connect that means slope. So when x is 0 on this graph, we can see that f prime is certainly equal to 1. So that is our particular slope. We know that f prime of 0 is 1. So again, from that, it's fairly easy to write an equation of a line in slope-intercept form, right? Because we have a y-intercept there. And then if we apply our step size, now we have to think about that. Let's see, we go from 0 to 2, and we're going to do so with 4 equal steps. So the difference between 2 and 0 is 2. Divide by 4. That indicates that our step size is going to be 1/2. So we apply that 1/2. We have a new x value of 1/2. And then to find that new y value, we have to go back to our previous line, plug in our new x, which is equal to 1/2, and then think, well, what's 1/2 plus 6? That's 6.5, or we could call it 13/2. If you want to work with decimals, you could use 6.5. Sometimes in these problems, believe it or not, I think it's easier to work with fractions than it is with decimals when you don't have a calculator. Now, as far as this slope, now we see our new x position is at 1/2, so we have to figure out what's f prime of 1/2, and that definitely takes us up here to the curve. We've got a very well-behaved curve that shows nice integer values along the y-axis for these various places that we're going to be stopping. And so we have a 2 there. So I'll just write one more lines equation just to kind of give you the general feel. Here's our point slope form. But as I said, you just basically keep this process going. And when you get down to the end, this 4 iterations, you're going to end up with eventually a 2, right? By the time you continually adding 1/2. And I'm gonna go ahead and tell you that the answer to this is 9. In other words, the approximation, and that's really important. We don't ever want to say that f of 2 equals 9. We'd like to say that f of 2 is approximately 9 for good math notation. But let's see if you guys, for homework, can fill in the gaps to get to that answer. Now, parts B and C, I'll work with you before I turn it over to Brian, are going to be a little bit quicker, a little bit easier. And part B particularly is going to invoke some AB content. Just simply asks, use a tangent line approximation at x of 2f of x, sorry, at x equals 0 to approximate f of 2. So you kind of look at this and think, well, what does this have to do with Euler's method? Well, it's really the first iteration. I mean, that's really all it's saying. You know, you have this 0.06, right? It says that f of 0 equals 6. We're going to use the tangent line when x is 0. And so then we want to find the slope specifically there. So you have to know that you're looking for the slope right there at the beginning. And we've already talked about that, right? That's that value of 1. And in fact, if you put these two ideas together, you might think, well, isn't that the very first line that we wrote in part A? It certainly is. The only difference to this problem is this is where we're stopping. If we want to approximate f of 2, we know that that's really approximately y of 2, which in this case is 8. And it's interesting to see that our final answer that we got for part A was 9. to approximate f of 2, but here we got 8. And it makes you think, well, which one do you think might be a little bit better? The one that allowed us to redirect that tangent line, I think, 3 additional times, or the one that uses the original tangent line? So if you're thinking that possibly that part A answer is a little bit more accurate, you're exactly right. So if we move into part C, boy, found a great way to infuse some previous ideas here. Find p sub 2 of x, the second degree Maclaurin polynomial for f of x, and evaluate p sub 2 of 2. So we are writing just a real quick polynomial. It's a Maclaurin, so that means that we are centered at 0. C is 0 or x is 0, and it is a second degree. All right, so if you kind of recall our setup there, we like to say that, okay, if we're going to put this p sub 2 together, it's going to involve finding f, evaluated at where we're centered, and then to that, we will add f prime where we're centered, times our x minus 0 to the first, or just x. And then we have our final term, which is going to consist of our f double prime of 0. That, of course, would be divided by 2 factorial and then multiplied by x squared. Now we just assemble and we find our f of 0, which is given in the stem here of the problem of 6. And then f prime of 0, I think this is now the third time that we're going to defer to that f prime of 0 being equal to 1. 1 times x, or just x. And then f double prime. Well, you don't want to really spend a lot of time looking at the graph here to figure out what f double prime of 0 is, because it's going to be very difficult. But if you continue to look at the stem of the question, f double prime of 0, it indicates that it is equal to 1/4. And if you divide that by 2 factorial and then multiply by your x squared, you're good to go. And of course, if you wanted to, you could simplify this. It simplifies pretty nicely to be, I believe that would be a 1/8 x squared if I did not do that incorrectly. I think that's what we get for that part C. Is that right? So moving ahead to part D, I think Brian's going to take over and show you some other nuances with this particular BC question.
Sure, sounds great, Tony. So this question, so we're not going to finish part D and E on here, but I want to make sure you know that it's there. This is why those links underneath the videos are so helpful, because there's so many good problems that you could do there. So part D introduces this idea of a geometric series. We get some convergence ideas in there, and we're going to get to do some integration techniques as well. So it's kind of a neat little problem. So take a look at it. Our friend Ted Gott is typing up the solutions. I think he might have called me and Tony evil yesterday because he types up these solutions. Will send us some questions. Or like, hey, what's going on here? And sometimes we just have errors on our initial papers. You might have even downloaded one of our documents that had a typo in it at first, because we're doing these every day and we can't catch every mistake. But a lot of times he's like, man, these are tricky, tough problems, right? So, and then part E goes into another idea of average value. So now we're connecting this back to some A/B topics and some of our integration ideas to find the exact value of f of 6. Right? We were approximating it earlier, and now we can come up with the exact value if we can use an average value problem. So make sure you try those, check the solutions, and see how they look. So what I want to do is get to BC number 4. So if you have your handouts with you, switch to number 4. I think it's a really important problem, and we're not going to spend a ton of time on it because you've gotten the idea of Euler's method, but there's a couple of twists here that I want to make sure you're aware of. Well, we see a graph in the stem, and Tony gave us a nice problem. We had a graph that we worked with in the last one, but it's a little bit different. And then our differential equation, right, is x times h of x. This is where reading carefully becomes an important idea, because our differential equation dy dx is for f of x. So f of x is connected to dy dx. If I could solve this differential equation, it would be giving me a solution for f. It just so happens that the differential equation is connected with this other graph of h. H is part of our derivative, and we have an initial condition of f of 3 equals -7, right? And so why is this problem so different? Well, it's not just because there's a graph and a couple kind of more conceptual ideas. It's because look what's happening. We're given f of 3, but we're trying to approximate f of 0. So this is the first example we've seen where we know a value of our graph at 3, and we're trying to go backwards this time instead of going forwards, right? Well, what does that do? Well, it changes your step sizes, right? Not just how long they are, but the direction of them. And so if we're starting at 0, we're starting at 3, sorry, our x value is 3, our y value is -7 to begin with. We want to approximate f of 0, right? So we're going to have 3 equal steps. So it's going to go down to 2, and then to 1 to 0. What does that tell you about h? Well, be careful. H is not 1, it's -1, right? Because we're going reversed with our x value. So you have to be really careful that if you're going backwards, you catch that nuance that h is a negative value in this case. And so if we were trying to solve this problem, we could go, we got to find y sub 1, our first y coordinate is going to be our starting y value of -7 minus 1 in this case, right? Times the derivative at our condition. And that's going to be x times h of x. Well, we know x is 3. And then h of 3 is going to be what we have to compute, right? And that's going to be -7 minus 1. And then we have this nice graph here to find h of 3. H of 3 is right here, which happens to be -1. And so our next y value is going to be -7 plus 3, which is -4. So we get -4 here. And then we would just continue that process, right? We would say, okay, our next y value is going to be our current y value. Our h doesn't change, is always the same. That's why they're always equal step sizes. But now we're taking the derivative at this location. So x is now 2. And then h of 2, according to the graph, is right here. H of 2 happens to also be 2. And we get -4 minus 4, which is -8. And then our final iteration, we're now at -8, and we still have the -1. Our current x value now becomes 1, and then h of 1 happens to also be 1 in this picture. And then we get -8 minus 1, which is -9. And so after all of that, we came up with -9 for our approximation, which means that according to Euler's method with this process, f of 0, like Tony had mentioned, is approximately equal to -9. So it's important to realize whether you're going forwards or backwards, pay attention to those details. Those little details come up a lot. Like if you're doing related rates, remember like related rates and Calc AB way back when they would give you some rates of change and they might slide in like something is decreasing at a certain rate, then you had to make the connection like, oh yeah, I got to make that number negative. It didn't write the negative on the paper, but the words indicated that the problem would have been a negative value. So on BC4, there's a couple more parts to it. And there's a couple of questions on part 5 that we would encourage you to check out, some really good problems. And we're not going to do BC6, but I want to point out just a couple things that are in here. So that way, when you try these problems later, you kind of know what you're getting into. So BC6 is starting the stem with the Taylor polynomial, right? There's no guarantee that if we see Euler's method on this year's exam, that the initial problem is going to be talking about differential equations, right? If we see a differential equation on the exam, that might be a hint that, hey, we might do Euler's method here, right? But what if the problem started with just some Taylor polynomial? So you kind of start in part A about making a Taylor polynomial. This would be a really good practice to review what Tony and I did on Monday as well as the last week or so. But then all of a sudden in part B of this question, the same Taylor polynomial, now we introduce this idea of Euler's method, because we're doing this Taylor polynomial with this function g, but then in part B, we introduce a new function f and a differential equation. And to do Euler's method, we have to know what that derivative value is. Well, notice our derivative of f is somehow connected to the derivatives of g, right? So g is generating this Taylor polynomial. So now we're going to make some really cool connections between developing Taylor polynomials and Euler's method with derivatives. So definitely try that one out and then compare your solutions with what we see in the drop box later on. So lots of good problems in there. Try them, right? Practice these problems because they're going to really test your true conceptual understanding of what's happening here. All right. So thank you so much. We're so glad that you were here. And Tony, I think you have some tweets for us today, don't you?
I do. They're still coming in, and we don't want them to stop. So if you have a teacher that you really want to recognize, make sure that you tweet out AP Teachers Rock, that hashtag, and we are going to recognize a Mr. Gilson. So please shout out Mr. Gilson from Central High, my AP Calculus AP teacher from last year. His teaching style is unmatched in terms of efficiency. He made me love calculus, favorite teacher of all of high school. Congratulations, Mr. Gilson. And for our AP Students Rock hashtag, we are now going to recognize this group of students. I want to give a shout out to all of my AP Calculus BC students. They're all studying and working together to prepare for the examinations despite these challenges. And we hope that all the students around, the United States, our friends to the north in Canada and outside of North America are feeling the same way. And as always, if you're having trouble from a technological standpoint, if you are not able to access the internet, or if you have friends who are in that situation, or they just don't have the hardware devices that they feel they can be successful when May 12th comes around, please have them reach out to the College Board at cb.org/tech, and they'll definitely take care of whatever issues that you or them might have. So great show today, Brian. I'm real excited. I'm already excited about tomorrow's show, Thursday. The topic is going to be logistic differential equations. You've heard a lot of things about flattening the curve. We're not going to tie this into what's going around us, because that's probably pretty cliche. It's something that maybe you've talked about if you've seen it on the news. But we're going to talk about a lot of logistic differential equations that can apply to various populations, various spreads of diseases in general. So definitely look forward to that, but we're going to infuse and embed some previous ideas into those as well. So with that, Brian and I, we are out, and we certainly look forward for tomorrow. And we want all of you to have a great day. And as always, stay safe, stay healthy, and keep learning.
Thank you so much, Tony. And if you didn't notice Tony's background, he changed it on me. And I think, Tony, I wonder if anybody at home figured out, it's kind of obvious to me now that I see the Kevin Costner in the background. So I'm going to go with, is that my Dancing with Wolves? Is that, am I on it?
It is Tatanka, Lieutenant John Dunbar, my favorite movie of all time. And special shout out for those of you that are in the plains. Beautiful country there, South Dakota and Wyoming. So you're very blessed.
Kudos to anybody that figured that out, especially on Tony's first background. So Anthony G is going to take us out, as always, with our outro AP Calculus song.
All right. Take care, everybody.
AP Calc, yes, AP Calc. Welcome here to AP Calc, yes, AP